Hello everyone, welcome back to my another new YouTube video. This video is in continuation with my previous video where I have solved problems of basic electrical engineering subject of module 1 and module 2 of VTU model question paper. So this is in continuation with that. So today in this video I'll be solving module 3, module 4 as well as module 5 questions of this model question paper. If you can see the PDF from module 3, we can see that 5C question which is of DC generator. So let us solve the problem of that. 4-pole 1500 RPM DC generator has a lap wound armature. So we can write the given data. So the number of poles P is equal to 4 and N is equal to 1500 RPM, and then a lap wound armature, which means that the number of parallel paths of a DC machine is equal to the number of poles having 32 slots. So there are 32 slots totally in a DC machine, and in each slot there are 8 conductors per slot. So if the flux per pole is 0.04 Weber, so phi is equal to 0.04 Weber. Determine the EMF. EMF is nothing but the generated EMF. EG is required to be calculated. Also, they have told what would be the EMF induced if the winding is wave connected. So you also need to calculate EG when the winding is wave connected in the sense A is equal to 2. So let us solve the first part of the question. As you can see that flux is given, poles is given, speed is given, you can apply the formula Eg is equal to phi ZNP divided by 60A. So this is a general formula to be applied. Now for a first case wherein it is the windings is lap connected, so A is equal to P. I can write it as phi Zn divided by 60, because P and A is also equal to P, that gets cancelled out. So remaining is phi Zn divided by 60. Now that is equal to, now phi is nothing but 0.04. Now what is the total number of conductors? You have been given that in a DC machine there are 32 slots, 8 conductors per slot. So if you multiply 32 into 8, you are going to get the total number of conductors, because in each slot there are 8. 8 into 32 will give you the total number of conductors in the machine. So 0.04 into 32 into 8 into 1500 RPM whole divided by 60. So the generated EMF you are going to get as 256 volts if you are solving this. So this is a generated EMF when it is lap connected. Now the same we are considering when it is wave connected. So the second part of the question we are going to solve. So EG is equal to the same formula phi ZNP divided by 60A. So I'll substitute this. EG is equal to phi is equal to 0.04. Z is equal to 32 into 8. Then N is equal to 1500. P is nothing but the number of poles, that is 4, divided by 60 into, in a case of wave connected armature, A is equal to 2. So 60 into 2. So if you solve this, we are going to get it as a 512 volts. So this is for wave connected armature. So this is how you solve this very simple problem of a DC generator. Now let us go to the next question. In the question paper, it is sixth question and sub question is C. And this is a problem of a single phase transformer. Rating of the transformer is given as 250 kVA. Then 11 kilovolt bar 415 volt, which means that the primary voltage is 11 kilovolt and the secondary voltage E2 is equal to 415 volts, and the frequency F is equal to 50 Hertz is given, and the number of turns has 80 turns on the secondary, which means that N2 is equal to 80. You need to calculate the first sub question, what is the primary and secondary currents. I1 is equal to question mark, I2 is also equal to question mark. Then the second part of the question, that is number of primary turns, you need to calculate En1. Next, you need to calculate what is the maximum flux of the core. Phi is equal to, you need to calculate. And the fourth one, voltage induced per turn on the secondary, you need to calculate what is E2 by N2, right? It is now voltage across the secondary per the number of turns across the secondary winding. So let us solve the first part of the sub question, that is primary and secondary currents. So since the number of primary and rated primary and secondary currents is asked, the rated kVA rating of the transformer is 250 kVA. So I can calculate I1 as equal to the kVA rating of the transformer divided by your primary voltage, because kVA, volt into ampere, divided by voltage will give you the current. So it's common sense. So it is 250 k divided by the primary voltage 11 kilovolt. So you are going to get the primary current as 22 point, if you solve this you will get 22.7272 amperes of the primary current. Similarly, I can calculate I2 is equal to the corresponding kVA divided by E2. For I2 it is E2, for I1 it is E1. So again it is same 250 kVA, K divided by, it is 415 volts across the secondary. You are going to get it as 602.4096 ampere. So very simple, you can easily score marks in this for the primary and secondary currents. So now they have told you what is the number of turns in the primary. Whenever it is asked, you can apply two formulas, 4.44 F5 N1 N2. Using that formula you can apply, but the problem is that you don't know what is the value of the flux. So but you know what is E2, what is E1, what is N2. So directly you can apply the voltage transformation ratio E2 by E1 equal to N2 by N1. So that implies E2 is nothing but 415 divided by 11 kilovolt, that is equal to N2 is nothing but 80, N1 is given. So that implies I am calculating the value of N1 as 21. If you solve this, you will get it as 2120.4819. So which is roughly equal to 2121 turns at the primary side. Then the third one is maximum flux in the core. So you need to calculate phi. You have the formula, general formula, or you can also give E1 is equal to 4.44 F5N1 at the primary side. Similarly, E2 is 4.44 F5N2 across the secondary side. Any formula, any of the two formulas you can apply. So any formula you can apply to get the value of the flux phi. So let me apply E2 is equal to 4.44 F phi N2 volts is a formula. So E2 is 415, that is equal to 4.44. F is nothing but 50 hertz is given. Phi is what you need to calculate into N2 is 80, which is given. So if you solve for this, cross multiply, so 4 phi is equal to 415 divided by 4.44 into 50 into 80, you are going to get the value of flux phi as phi is equal to 0.0233 Webers. So this is a value of the flux phi what you're going to calculate. And the last one, it is the number of the voltage per turn across the secondary. So it is E2 by N2. So that is 415 divided by N2, that is 80. So in each turn you are going to get 5.1875 volts. So this is how you are calculating the fourth sub question, which is very simple to calculate. Coming to the next, module 4. So in the model question paper module 4, it is 7C question. So let us see how to solve this problem. 12 pole, so this problem is of induction motor. 12 pole 3-phase alternator is coupled to an engine. So engine running at 500 rpm, it supplies an induction motor which has a full load speed of 1440 rpm. Determine the percentage slip and the number of poles of the motor. Now it has been given that the induction motor is supplied by the alternator. So alternator is there. So now that feeds your induction motor. So as you know that the input to the alternator is through the engine which is running at 500 rpm. Okay, so the output from the alternator is a three-phase supply. Three-phase supply, if you are considering a three-phase induction motor, and then the induction motor output is a rotation now for a induction motor. So it has been given that the alternator, the number of poles in the alternator is 12, and it is a three-phase alternator is coupled to an engine at which is running at 1000. The alternator is running at 500 rpm. Okay, so now this is supplying to an induction motor which has a full load speed of 1440 rpm. So if I am calculating that the speed of an induction motor is n, the speed of an induction motor is n, which is running at 1440 rpm. Determine the percentage slip. Yes is equal to question mark, and the number of poles of the induction motor you need to calculate. Now with this given data, what can you tell? We can see that the induction motor is running at a synchronous speed. We know that the induction motor synchronous speed of the induction motor is given by 120 f divided by p, where f is the supply frequency, but we don't know what is the supply frequency, so we need to calculate what is f. So we need to calculate what is f. So for that, we have an alternator which is running at n and p. We also know that the frequency of alternator f is equal to n p divided by 120, where n is the speed of an alternator, p is a number of poles in an alternator. So na is nothing but 500 rpm, which is given. Number of poles is 12 divided by 120, so you are going to get it as 50 hertz, which means that the output AC, the three-phase supply, has a frequency of 50 hertz. Now what you have to do now over here is, you cannot directly calculate ns because the number of poles you don't know, which is the question which is asked here. So if I consider that, if we assume that there are two poles, if there are, because for the synchronous speed ns, minimum number of poles there should be. If there are two poles, one north and one south, for the generation of a magnetic flux, so if there are two poles, that is p is equal to 2, because this is a minimum number of poles which is required. What you are going to get ns as? Sorry, so you are going to get the number of poles over here, ns, as equal to 120 into 2 divided by 120 f divided by sorry, frequency is 50 hertz, so 120 into 50 divided by 2, so you're going to get it as 3000 rpm. Now with this ns, if you're calculating the slip, so slip will be equal to ns minus n divided by ns. That implies ns is nothing but equal to 3000 minus 1440 divided by ns. Ns is 1440. So roughly you are going to get it as 0.52 or 52%. But for a machine, for a smaller motor, your slip cannot be, for small motor, your slip cannot go, slip maximum is 5%, maximum is 5%, and for larger motor, the slip is roughly equal to, nearly equal to 2%. It cannot go beyond that. So the number of poles is equal to 2 is not possible. Now if I consider that the number of poles p is equal to 4, if p is equal to 4, then you are going to get ns is equal to 120 into 50 divided by 4. If you use that, you are going to get the speed as 1500 rpm. So with this, if I am calculating the slip, therefore the slip will be equal to 1500 minus 1440 divided by 1500. So you are going to get it as 4% or 0.04. If you convert to percentage, it will be 4%, which is within the admissible limits, which means that your first answer, the number of poles in the induction motor should be equal to 4, and the slip is nothing but equal to 4%. So this is how you are attempting these kind of problems. Coming to the next problem, which is of 8c. Again, this problem is of alternator. So it is given that the number of poles in the alternator is 12. The speed at which the alternator is rotating is given as 500 rpm. Alternator has 48 slots are there, and 15 conductors per slots are present. per slot is present. The flux per pole is 0.02 Weber, and which is distributed sinusoidally. The winding factor is 0.97. Winding factor is also nothing but distribution factor, which is 0.97. EL is what is asked in the question. So for that, first you have been given all these things. Okay, so what is the formula to calculate the phase EMF? EP is equal to, you know that it is 4.44. For an alternator it is 4.44 F5T Kc and Kd. Okay, the EMF is decreasing because of these two factors, 4.44 F5T. Now you don't know what is the frequency, but you know what is the speed and the number of poles. So the first step is you have to calculate the frequency. NP divided by 120, which is nothing but equal to 500 into 12 divided by 120. So you are going to get it as 50 hertz. So this is the frequency. So this part is already done. Flux is already given. You need to calculate what is T. T is nothing but, you know that it is number of coils per phase. Okay, so which is now equal to Z divided by 2. Z is nothing but the total number of conductors. So, and since I am calculating per phase, I also need to calculate Z is equal to total number of conductors per phase. I need to calculate over here because it is given everything in 3 phase. So now that is equal to, how to calculate total number of conductors. In the question it is given there are 48 slots in a machine alternator and there are 15 conductors per slot. So what can you calculate? The total number of conductors will be 48 into and 15 conductors per slot. So you are going to get the total number of conductors for 3 phase. But the question is, per phase I need to calculate. So since it is 3 phase, per phase I divide it by 3. So if I divide it by 3, I am going to get Z as equal to 48 into 15 divided by 3. I am roughly going to get it as 240. So this is a total number of conductors per phase. Now I need to calculate what is T. 240 divided by 2, that is equal to 120. Please note that don't divide again 240 by 3. The reason is I have already calculated the total number of conductors per phase, that is divided by 3. So coils T is also equal to number of coils per phase, which is already present, which is nothing but 120. So once you calculate T, so you can directly calculate the EMF as 4.44. F is nothing but 50 into 5. 5 is nothing but 0.02 and T is nothing but 120. Kc is 1. If it is not given, assume Kc as equal to 1, which is nothing but pitch factor, and distribution factor or winding factor, it is given as 0.97. So you are going to get over here as 516.816 volts. Now all the EMF you have, conductors, everything you have calculated per phase. So even the EMF which is generated will also be the phase EMF which is being generated. You need to calculate the line EMF. In the question it is given that it is a star connected alternator. So you know that in a case of star connection, line EMF is equal to root 3 times phase EMF. So just multiply the answer with the root 3, 516.816. So you are going to get the voltage as 895.1515 volts, which is the answer for the given problem. So this is how you solve the alternator problem using the formulas. So which are the formulas? One is E is equal to 4.44 F5T Kc Kd, and to calculate the frequency F is equal to 1 NP by 120, and then you need to calculate T is equal to Z by 2. Z you need to calculate per phase, so it is for number of slots into number of conductors per slot divided by the phase, so divided by 3 you need to calculate. So this completes your module 3 and module 4 problems. Coming to the final one, that is module 5. Module 5 problem. A consumer has a maximum demand of 200 kilowatt at 40% load factor. If the tariff is rupees 100 per kilowatt, you need to calculate the overall cost per kilowatt hour. So this is a tariff problem, electricity. So you need to calculate the tariff. You know that in a two-part tariff, C is equal to AX plus BY. So where AX is nothing but the fixed charges. Okay, so fixed charges, And now By is a running cost, which is nothing but based on the electricity consumption, running cost. So what is A? A is nothing but cost per kilowatt of maximum demand. X is nothing but maximum demand. X is maximum demand. Similarly, B, it is cost per kilowatt hour of the energy consumed, and Y is nothing but the energy total units of energy consumed. So these things, if you remember, then the problem becomes very easier for you. Now first and foremost, first we will calculate what is a fixed charges for the given problem. So you know that the consumer has a maximum demand of 200 kilo. X is nothing but maximum demand. So maximum demand X is equal to 200 kilowatt. And next, load power factor we'll see later. If the tariff is rupees 100 per kilowatt of maximum demand, A is nothing but cost per kilowatt. So A is nothing but rupees 100 per kilowatt of the maximum demand, and maximum plus 10 paise per kilowatt hour. So what is Y? Y is what is B? Cost per kilowatt of watt hour of energy consumed. So your B is nothing but 10 paise. 10 paise is nothing but 0.1 rupees per kilowatt hour of the energy that is being consumed. You need to find out what is overall cost per kilowatt hour. You need to find out C for the total energy which is being consumed, C per kilowatt hour. So how do you solve this problem now? So first and foremost, you need to calculate what is AX. AX is nothing but your fixed charges unit will also always be in rupees, right? So fixed charges, that is equal to A is already given rupees 100 per kilowatt into, and x is nothing but 200 kilowatt. So you're going to get this as rupees 20,000, right? So kilowatt gets cancelled, so remaining is rupees 20,000. So that is a fixed charges. Now I need to calculate, B is already present. I need to calculate Y. Y is nothing but what is the total units, total number of units consumed. So consumed, the unit is what? Kilowatt hour. So that is now equal to kilowatt hour. You need to calculate kilowatt. So now you have this power. The rating is given, which is nothing but 200 kilowatt. So 200 kilowatt is the maximum demand into, you need to have the power factor VI cos phi. So cos phi is nothing but over here 40% load factor. So your power factor is nothing but cos phi, that is given as 40%, or it is equal to 0.4. So VI cos phi is nothing but the power consumed into hour, number of hours the energy is being used. So if you are calculating for an year, it is 365 days into 24 hours. So if you multiply 200 kilo into 0.4 into 24 into 365, you will get the total energy that is being consumed over here is roughly around 7 lakh 800 kilowatt hour of energy that is being consumed. So if you are calculating By now, that is nothing but running cost, which is again will be in rupees only. So B is given already, that is 0.1 rupees per kilowatt hour into 7 lakh 800 kilowatt hour. So if you multiply this, you are going to get it as rupees 70,800 rupees. So that is your running cost. So now you have to calculate the overall cost. C is equal to AX plus BY. Now that is equal to AX you have calculated as 20,000 rupees plus 70,800. So roughly you are going to get it as 90,800 rupees you are going to get as a overall cost. Now they have asked overall cost per kilowatt hour. So overall cost per kilowatt hour of energy that is being consumed, that is 90,800 divided by, so 7 lakh total energy consumed is 7 lakh 800 kilowatt hour. So you're going to get the amount as rupees 0.1285, or I can also write it as 12.85 paisa. So this is how you calculate the problem. So this finishes off all the problems of model question paper 1 from module 1 to module 5. Hope you have liked this video. If you like it, please hit the like button and share with your friends so that this can be useful. I'm always open to feedback. You can also give the feedback in the comment section. Thank you.